Good morning, everyone. Welcome to the November webinar. We have a large audience joining today, so we will take a minute to cover a few housekeeping items and then introduce our speaker. For everyone in the audience, you can ask the speaker questions at any time during the webinar by entering the questions into the questions box on your GoToWebinar side panel. Our speaker will be taking the questions at the end of the webinar, but feel free to enter the questions at any time. We have a special guest speaker this morning. Dr. Hu gave a webinar earlier this year, and we have asked him back to present his recently published work on variability and uncertainty. And we are really thrilled to have him. For those of you who have not seen his paper, the reference will be showing up on your screen shortly. Dr. Hu is currently a senior scientific director and fellow at clinical pharmacology and pharmacometrics at Johnson & Johnson in the US. He obtained his PhD in operations research and completed a postdoctoral fellowship in clinical pharmacology research at Stanford University. His career began as a statistical reviewer at the Office of Biostatistics, the FDA, in 1996. Subsequently, he has worked in consulting Farsight Corporation, clinical pharmacokinetics at GlaxoSmithKline, and at Biostatistics Sanofi, before joining Centocor, a subsidiary of Johnson & Johnson in 2007. His main research interest is in pharmacometrics methodology development to enable parsimonious predictive PK/PD modeling for the purpose of guiding clinical dosing regimen decisions. So I would like to give a very warm welcome to our speaker this morning, Dr. Hu.
Thank you, Rebecca, for the very kind introduction. I would like also to thank the organizers to share my view on this important topic that pharmacometricians regularly face. I will now turn off my camera to better focus on the slides. This talk is based on this commentary that has appeared recently in JPK-PD. I understand the views on this topic can be diverse, so I plan to speak for a little less than half an hour and leave plenty of time for discussion. On this topic, pharmacometricians may be put into two buckets: those who know they are confused about something, and those who think they know everything. I, for one, has been thinking about writing this paper for over 10 years. And yet I find myself changing my recommendations even 2 weeks before submitting the paper. So, at least for me, the topic's quite sophisticated. Here's a quick motivation of the problem. In MIDD, pharmacometricians usually produce model predictions along with intervals. The question is, what does an interval represent? Is it variability, uncertainty, or both? And what should they actually represent? And furthermore, how often do you think the author and audience interpret them the same way? Any ambiguity on this obviously will jeopardize drug development decision-making. In case you're wondering, what is the big deal? Uncertainty and variability are very different things. Uncertainty, and for the sake of simplicity, I shall mean estimation uncertainty for the most part of this talk. It is reducible by having more data. You can imagine if you have all the patients in the world, your uncertainty will be 0. It is useful for statistical inference or hypothesis testing, and therefore formal decision-making. Variability, on the other hand, cannot be reduced by having more data. In other words, when you get more data, you would expect your variability estimate to be roughly the same instead of going up or down. It does not reflect uncertainty on the mean or the typical value, and it is not useful for statistical inference or hypothesis testing. In particular, then, it is not suited for formal decision-making. In this talk, I will first define the terminologies I will be using, and I will propose a relatively simple guideline on when to use which interval. It is likely simpler but different than what you might think. Finally, I will discuss some common misusages and misconceptions. This slide shows some notation that every pharmacometrician knows. We begin with a nonlinear mixed effect model with parameters of fixed effects between subject variability, BSV, and residual unexplained variability, which is oftentimes called residual error, meaning that it's not real. This has implications on simulations, as we will discuss later. We also assume that the uncertainty distribution is available as obtained through variance covariance matrix of parameter estimates, or bootstrap. Now we come to the difficult part of the terminology, namely the definitions of the intervals. This slide may be the second most important of the whole deck in that once everything on this slide is fully understood, half of the simulation interval guideline will just naturally follow. The statistical definitions of confidence interval and prediction intervals are briefly given here. Most pharmacometricians do not fully understand them, and it is not my intention to try to fully explain them in a few minutes. Rather, I will offer a few practical characteristics to help determine when to use which intervals. Confidence interval refers to a fixed quantity, such as the overall population mean, and prediction interval refers to a future observed quantity. The confidence levels of confidence interval and prediction interval include uncertainty, and they are coverage probabilities under repeated experiments. They are useful for statistical inference, and therefore formal drug development decision-making. Visual predictive check, or VPC, on the other hand, only visually compares observed data with model predictions. They do not account for uncertainty, as you all know, so the intervals have no associated statistical terms. In particular, they have no coverage probabilities like confidence interval or prediction interval, and they are not usable for statistical inference, and therefore drug development decision-making. Remembering these characteristics will go a long way in helping knowing when to use which interval. Abstract definitions can be difficult, so now let us see how the different intervals can be actually simulated. What's shown here is a general pharmacometric simulation scheme. There are essentially two layers. The first layer is the trial layer, where a certain large number of trial replicates are generated, and for each replicate, a different set of model parameters are sampled from the uncertainty distribution. In case uncertainty is not used, the set of parameters will just be the same across all trial replicates. Next layer is the subject layer, where for each trial replicate, a fixed number of subjects are simulated from the BSV distribution. Then residual error may be simulated, and with all these, the model predicted response for a subject is given. Within the trial, then, using all the subjects, a summary statistic is formed, such as p-values or probabilities of trial success. Finally, we get a set of summary statistics for each replicate of clinical trial. Then these can be used to form model predictions as well as the intervals. Now we are ready to see how the most useful intervals are constructed. We begin with an interval that everyone is familiar with, VPC, which uses between subject and residual variability. The number of subjects is just the same as in the dataset. The interval represents variability. The prediction interval is constructed much like VPC, just by adding uncertainty on top of it. The interval represents variability and uncertainty. You can flip this around by saying that VPC is constructed like a prediction interval by removing uncertainty. The confidence interval is constructed very differently. It uses between subject variability when the parameter of interest is the mean of the response of the population. It does not use residual error, but does use uncertainty. The number of subjects should be large to calculate the mean accurately. The interval represents uncertainty. A special case of confidence interval construction is when the mean response is about the same as the typical subject's response, in which case BSV does not need to be used in the construction, and the interval still represents uncertainty. As we shall see, these are all the interval types of interest. A way to remember the difference is that VPC represents variability, confidence interval represents uncertainty, and prediction interval represents both variability and uncertainty. When to use which type of interval will depend on the application scenario. We begin again with an application scenario that every pharmacometrician is familiar with, namely visual model diagnosis. The objective here is to visually compare observed data and model predictions. The right interval to use here is VPC. The second application scenario is to inform future trial outcomes. The typical objective is for sample size planning. For such purposes, uncertainty is needed to understand the decision risks. The appropriate interval here to use is the prediction interval. The third application scenario is to inform population-level decision metrics, such as the mean response in the entire patient population. For such purposes, the residual variability, interpreted as error, is irrelevant and should be excluded. Uncertainty should be included to understand the decision risks. The appropriate interval to use is the confidence interval. The fourth and final application scenario is a special case to the previous one. That happens when the population-level decision metric is about exposure differences. In such situations, the population mean response is about the same as the typical subject. The typical application is covariate-based dose adjustment or exposure matching. These are typically bioequivalence type of evaluations. In such situations, the appropriate interval to use is the confidence interval. The difference with the previous scenario is that BSV is not needed because the population mean is about the same as the typical subject. This gives the complete classification of simulation intervals and usages. The number of interval types may seem surprisingly small, considering the large number of possible combinations of between subject variability, residual error, and uncertainty. To better appreciate the use of variability and uncertainty in the application scenarios, let's look at these scenarios in more detail. In model diagnosis, the interest is in diagnosing the existing model without uncertainty. Therefore, the interval has only variability, as in the VPC interval. The remaining application scenarios deal with drug development decision-making, for which the understanding of uncertainty is important. If the interest is with a future trial of a fixed number of subjects, that incurs variability. Therefore, the interval contains both variability and uncertainty, as in the prediction interval. If the interest is not in a future trial with a fixed number of subjects, then the interest lies in the entire patient population, namely the population-level decision matrix. BSV may be used in the calculation of such matrix, but these matrices have no variability associated with them in and of themselves. Therefore, the interval consists of only uncertainty, as in the confidence interval. The fourth application scenario is just a special case of the third one. Therefore, these scenarios covers all interests of applications, and violations of the table are misusages in principle. We now discuss some common misusages and misconceptions. The first misusage is to use VPC where prediction interval should be used instead. This occurs partly because of terminology confusion in pharmacometrics. Because VPC intervals are narrower than prediction intervals due to the ignorance of uncertainty, this may result in overly optimistic decisions. The second misusage, which occurs quite often, is to use BSV instead of uncertainty, such as in population PK covariate effect forest plots, where the covariate effect 90% confidence interval are plotted against 80-125 reference lines. Such assessments are essentially bioequivalence-like. But in practice, pharmacometricians often use BSV to construct the interval instead of uncertainty. Such intervals are not then confidence intervals, which are invalid for statistical inference or hypothesis testing, and therefore is not appropriate for bioequivalence type of claims. The next misusage is related to the previous one. Often, pharmacometricians are asked to produce the percent of subjects achieving certain concentration threshold under a dosing regimen. So they go ahead and produce the number to their superiors and get asked the question, well, here's your prediction, where's your interval? So then they go back and produce an interval using variability from an arbitrary number of subjects. So they repeat this number many times and construct an interval from some percentiles of all these replicates. The problem with the approach is that the interval will become smaller when the number of subjects becomes larger. So the interval they produce is really meaningless for decision making. The root cause for this problem is confusing variability for uncertainty, which is related to the previous one, just takes a different form. The next misusage occurs mostly for those who are trained in statistics. The thinking is, because uncertainty affects decision making, somehow it should be diagnosed. So the thinking is to use prediction interval for this purpose. Unfortunately, that does not work. The reason is that prediction interval is wider than VPC. So if VPC is expected to match with the data, then prediction interval cannot. The real reason for this is that prediction interval coverage is meant for future data. Therefore, it is too wide for current data. An investigation on this matter has actually been conducted over 2 decades ago. Many pharmacometricians know this paper here for introducing the term posterior predictive check from Bayesian theory. The paper is difficult to read in my opinion, but in essence it showed that neither VPC or prediction interval could be used to formally reject models. Now we turn to some of the common misconceptions occurred in pharmacometrics. The first is with the interval using only BSV. This is related to the misusage of the interval in population PK covariative effect forest plots as shown earlier. This interval is also often used in other PK simulations, and it is fine if the intention is to just show variability. But for this purpose, the interval functions only like a point estimate. As the common statistical saying goes, it is useless to show only a point estimate without uncertainty. In other words, the interval does not infer uncertainty of the middle point or typical value. Therefore, it serves no inference purposes, and it is not suited for decision making. In principle, if the variability is important for decision making, then its uncertainty should also be shown. For example, say that your simulation has shown that 80% of the population have trough concentrations between 1 and 10 microgram per ml. In other words, 1 microgram per ml is the 10th percentile, and 10 microgram per ml is the 90th percentile. Then, confidence intervals for these percentiles should also be shown. For example, 1 microgram per ml may have a 95% associated confidence interval of 0.8 and 1.25. Likewise for the 10 microgram per ml. More generally, when an interval only serves as a point estimate, its uncertainty should also be shown. The second misconception has to do with what is meant by including both uncertainty and variability. Sometimes this is done by mixing uncertainty and variability, say BSV, by first simulating a large number of replicates. Each replicate has a large number of subjects, and then mixing all the subjects across all replicates as if they all come from one big population. Many pharmacometricians find this intuitively appealing. The problem is that the so-called population distribution is not statistically interpretable. One can see the problem by that the subjects are not independent from each other. The best way to see this may be to try toy simulations with different variability magnitudes to see how it behaves. The root cause of this problem is that uncertainty is at a higher level than variability, say BSV, and it actually includes BSV as a parameter. So the two cannot be combined together as if they are two different independent variability sources. To phrase this in the language of the general simulation scheme shown earlier, subjects in each replicate must be first used together to form a summary statistic at the level of the replicate, and they should not be mixed with all those other subjects in other replicates. The next misconception I'll cover is whether to use the typical or the mean response. Often in drug development decision making, the typical subject response is the one that's been simulated. However, the decision matrix is most often the mean response, and therefore the mean is actually the decision metric that should be simulated. The last misconception I will cover is with the simulation objective. Say that we want to understand an interesting quantity, such as the percent of subjects achieving certain concentration threshold. And the claimed objective is that we also want to account for uncertainty. So with that stated objective, a simulation distribution can be constructed using both uncertainty and BSV by first generate many trial replicates from uncertainty and use only one subject per trial replicate. This will give us many subjects from which we can construct an interval, say, using 5th and 95th percentiles. This interval actually has a statistical term called tolerance interval, which is mostly used in quality control settings. But for drug development, there's a better objective, namely simply the quantity of interest, say percent of subjects achieving concentration threshold, and its uncertainty. So this will lead us to the common confidence interval. What's important to pay attention in this case is that we should not only be satisfied with that our simulation or intervals are interpretable, but whether it is the best or most relevant for decision making. Now let's talk about some limitations and issues on what we have covered so far. For sake of simplicity, we have not discussed all variation sources, but similar principles should apply. For example, interlocation variability can often be treated the same way as in between subject variability as in the guideline. Next, the guideline represents an ideal in that, in practice, you may choose to deviate from it for reasons of convenience. While that can be understandable, the limitations should be clearly recognized. In particular, if the situation deviates from the guideline, then it is preferable to state clearly what the interval represents, whether it's variability or uncertainty, to avoid confusions. Finally, prediction uncertainty is something that can be difficult to fully assess. For example, if outliers have been removed, that likely leads to underestimating uncertainty because outliers are part of life. There are also other factors, one of which I will get to next. There are different kinds of uncertainties, and one of which is due to model selection, which is common in pharmacometrics. Using estimation uncertainty based on only the final model will underestimate uncertainty of model predictions and may lead to overly optimistic decisions. Assessing uncertainty, accounting for model selection, is conceptually possible but practically difficult, and limited investigation has appeared in statistical literature. A possible remedy into the future may be confirmatory analysis. Confirmatory analysis for population PK has already been proposed. And even for longitudinal exposure response modeling, with enough experience, it is also possible, especially for late-stage clinical trials. The number of rational choices may be very limited. Even in situations when full confirmatory analysis is not possible, consciously limiting the amount of model exploration should still help in keeping uncertainty in check. Now, after seeing all the misusages, misconceptions, and limitations, let's revisit the proposed classification of simulation intervals and characteristics and see whether we can make better sense of it. First, if the application scenario is about model diagnosis, then the right interval to use is VPC. Hope that's clear for most pharmacometricians, since that's what they are already doing. If the application is not a model diagnosis, then it is about drug development applications, for which the understanding of uncertainty is important. That leaves us with prediction interval and confidence intervals. If the application is about understanding future trial outcomes, then the interval to use is the prediction interval. Otherwise, the application is about understanding population-level decision metrics, for which the right interval to use is the confidence interval. So there are really only total of 3 application scenarios with the 3 corresponding intervals to use. Well, there's a 4th application scenario given here. It is really just a special case of the 3rd scenario, for which the construction of confidence interval is simpler. Hope this helps to understand why the guideline makes sense. Because the topic is so basic and fundamental in pharmacometric daily practice, I understand that people may have very different opinions out there. I will be happy to address any questions or comments at this time. Thank you.
Thank you, Dr. Hu, for a very interesting talk. I know that we do have some questions. I'm going to start with the first couple, which are somewhat theoretical, but you defined variability and uncertainty, but isn't the variability really part of the uncertainty?
I'm not sure what that means. It may just be an interpretation of the terms. I guess if you call everything the same thing, then there's no way to distinguish them, and therefore their usages.
You mentioned that uncertainty can be reduced by adding more data. However, can uncertainty really ever be reduced to 0? Doesn't that actually require that you know all of the uncertainty?
That is an interesting question. As I mentioned earlier, for the most part of this talk, by uncertainty, I mean estimation uncertainty, which in theory, if your model is correct and you have an infinite amount of data, then it does become 0. In practice, you have other kinds of uncertainties, but those are not the kind that we can quantify and therefore simulate. So it is probably a bit pointless to talk about them, but it is perhaps important to realize that they exist. But for the purpose of constructing intervals and interpreting them, it's probably not too useful.
Could you repeat the approach in the event that the number of patients achieving a target effect is to be computed? The probability of technical success. Sorry, I'm mixing them. Could you repeat the correct process for simulating the % patients above a certain response threshold? Sorry.
Yeah, let me go to that slide. See, yeah, perhaps this one. There are a couple of misusages, but the right one here is to show the variability as well as the uncertainty of the variability.
For slide 32, could you please clarify if uncertainty is uncertainty of fixed effects or uncertainty of both fixed and random effects?
as mentioned in the beginning, uncertainty here refers to estimation uncertainty, and that covers both fixed and random effects.
So what
Keep in mind that random effects themselves represent variability.
What would you call the interval spanning, e.g. the 5th to 95th percentile of a population?
The most common one used by pharmacometricians is probably just constructed by only variability. So those are what I call interval using only BSV, which does not have a statistical term. So however term you prefer to use in practice, that's up to you, as long as that concept is accurately communicated.
When performing simulations including uncertainty, should we always include it in both fixed effects and random effects? If our RSV are less than 15%, could we state that the parameters are precisely estimated and avoid adding uncertainty to the model simulations?
Well, if it comes to prediction intervals, that's probably the only one that has that includes both variability and uncertainty. And if uncertainty is dominated by variability, then for practical purposes, it can be used as an approximation to ignore uncertainty.
Could you kindly clarify the correct interval to use, or the correct interval to reflect or illustrate in a forest plot? Is it both the uncertainty and variability?
The correct one to use is using uncertainty only. I remember seeing a view of using both variability and uncertainty in there. I suspect that's due to the misconception as mentioned here. In other words, I really don't see how a legitimate use of both variability and uncertainty could be constructed in that regard.
Could you, okay, so this question is, and I'm going to paraphrase, asking if you want to estimate the computed probability of technical success. I think they are referring to your last slides when you talked about the different intervals.
Yeah, I think here the summary statistic can be a probability of technical success. Yes.
And they ask if you could explain the approach for this.
Well, there's a it's not immediately coming to my mind, but it's well defined out there. I think Ken Kowalski probably first used them. There's a number of articles, so if you just Google probability of technical success, I'm sure it will come up.
What is the recommended method to compute parameter uncertainty?
The common ways are using, I think I mentioned here, yeah, either variance covariance of parameter estimates or bootstrap. So each has their pros and cons. Using variance covariance matrix of parameter estimates essentially uses a normal distribution, and to use that appropriately does have some practical consequences. In particular, the positive parameters will be best log transformed, and if there are any covariances between random effects, they will also need to be reparameterized for the intervals to remain in legitimate range. And Bootstrap does also have its assumption also. It can be bad with just a few number of subjects, say 50. And it will also require proper stratification, namely all variables should be exactly as in the study design stratification. In practice, people often stratify too many variables, which lead to underestimating uncertainty.
And I have a question myself, which is, there was a tutorial on forced plots in the November issue of CTP PSP. It had recommended two approaches, one using only uncertainty and the other using both uncertainty and BSV for future population. This seems, the one method seems consistent with your guidelines, but the other does not. Could you comment on that?
For the reasons I explained, deviating from the guideline is usually problematic, and this case seems no exception. If I understand that correctly, the first use of the using uncertainty only is what I recommend in the guideline here, but the second use is not, and that seems to be due to the misconception of mixing uncertainty and BSV as shown on this slide.
And one audience member asked, just a point, it may be worth pointing out that there is uncertainty in the estimate of variability, hence the need to account for both when making population inferences and making decisions. Would you agree with that?
Well, if that refers to estimation uncertainty of the random effects, that's already covered here. But if you are, if the question asks about the uncertainty of the uncertainty estimates, then we can go on infinite loop down that road. I'm not sure that's productive.
Now, you've used uncertainty and discussed it as part of decision making. When you present information for decision making, do you often present only the uncertainty, or do you show both the uncertainty and variability and define what each one contributes?
Yeah, again, I guess that comes to the guideline here in what is the intended use. Again, this is all shown in concept or in principle, and the only thing that has both variability and uncertainty here is the prediction interval. So so it has to be really used for the right decision metric.
And for BPC, one question that came up is BPC intervals, are those the same as degenerate prediction intervals?
Yes, I think that's a better term for statisticians. It can come out natural to them, but a more informative choice for pharmacometricians could be called VPC as prediction interval without uncertainty.
With the classical Monte Carlo simulations often seen for dose selection or PK/PD target attainment, is the uncertainty taken into account?
For what I've seen, commonly not, and and again, in principle, they should be. However, obtain uncertainty properly for all those models that have been used can be difficult, but that's a practical problem, although an important one.
Would you consider the RUV in simulations in addition to the uncertainty and BSV?
Again, it depends on the usage. Look at this table or guideline here. RUV is used in prediction interval only, so that's regarding future trial outcomes. For other purposes, such as population level decision metrics, as tried to explain earlier, RUV is something, if that's interpreted as an error, then that should not be included.
So Dr. Hu, one of the audience members has asked if you could show your first slide where it gives the reference for your paper. So, so we have a few more questions. The FDA seems to accept simulations ignoring parameter uncertainty. Has the speaker confronted, or let's see, sorry. I'm going to read this directly as it is. The FDA seems to accept simulations ignoring parameter uncertainty. Have the speaker confront clinical pharmacologists pushing back on using parameter uncertainty?
I've seen FDA accepting all sorts of things. I have worked for the FDA myself and understand there's certain heterogeneity in there. But I would guess presenting more is less likely to be rejected or objected. But if you include less, then it should be, in theory, that runs perhaps more of a risk.
Do the same issues apply to prediction corrected VPCs as they do for general VPCs? Sorry.
Well, again, it depends on the usage. If the purpose for prediction corrected VPC or PC-VPC is also a form of VPC, and that is for model diagnose only in principle. So again, in principle, if that interval is used for development decision making, then it is at least in principle not appropriate.
You said variability cannot be reduced by increasing sample size, but do more patients bring more informative information to enable variability irradiation?
Yes, more patients will make the estimation of variability more precise. But a priori, when you bring more patients, you would not expect the estimate size to go up or down. You would expect them to stay roughly the same.
Any ideas on how to incorporate all uncertainties of a sequential PK/PD model where the correlations between PK parameters and PD parameters are not estimated?
Sorry, could you repeat the last sentence where something are or are not estimated?
So the full question is, any ideas on how to incorporate all uncertainties of a sequential PK/PD model where the correlations between PK parameters and PD parameters are not estimated?
Well, in principle, that can best be accommodated only with a simultaneous estimation approach. But in practice, one has to go by assuming those parts are independent. So thereby combining PD model estimation uncertainty and PK model parameter estimation uncertainty together as if they are separate. In my experience, it's often not a bad assumption, but that is an assumption that one has to make, probably, I should add.
So you mentioned adding more patients to reduce uncertainty. Often early in drug development, there's not a lot of patients. Is there any other way to reduce the uncertainty?
One could do what that's probably done already by including, say, as much information, say, from literature or related compounds and so forth. Obviously, those kind of uncertainty cannot be formally quantified, but practically it should be a useful thing to do.
And on that note, we actually have two questions about rare diseases. So I'll ask the first one and then the second. So in cases of rare disease with limited data, when we run simulations for prediction of future trials, do you have a preference of using bootstrap or var-covar approach?
Yeah, again, it depends on the sort of data the model is built upon. Both approaches, as I mentioned a few moments earlier, answering a different question, has their specific pros and cons. Obviously, if you have time, you could try both and see what the difference might be. But variance covariance matrix is probably a bit at least easier to use.
And the second on the rare diseases goes back to uncertainty, and I think the definition of uncertainty as you've given it, where you may have the question asked, in rare diseases you may have actually all of the population with that disease, and yet the uncertainty would not be zero. How do you deal with that in looking at your matrix and understanding?
Well, in principle, if you have all the population, then your uncertainty is zero, even though there may be a sort of a standard error also associated with the estimate. But since we have everything, you will not have assuming that your future in the future your population will not change. Then your uncertainty actually is zero. But obviously, that's not accounting for other type of uncertainties, such as if patient's condition change and so forth. Those are the kind of uncertainties that are not really quantifiable.
I am just we have a lot of questions. I want to make sure that we've covered them all. And I had one. You mentioned using the prediction interval for future trial outcomes and the confidence interval for evaluating for the decision matrix or decision metrics. Is there any time when you might consider using the prediction interval in decision making rather than just for future trial outcomes?
No, and I guess that probably refers to. Let me see. I think I covered a misusage in. Let's try to see where that one is. Yeah, probably comes down to this one. So when you use prediction interval, you need to choose the number of subjects, but where does that number come from? And people sometimes choose say, hey, well, that's one that may come in one of the possible future trials, but the variability associated with that really depends on the number of subjects you choose. So when you use that approach, the variability term contribution becomes arbitrary and therefore meaningless.
Okay, so in a phase 1 trial, the population is often homogeneous, which may result in an underprediction of both uncertainty and variability. Do you have a suggestion on how to deal with this when simulating future trials or an outcome for a patient population?
Not formally. You probably have to sort of arbitrarily blow up the uncertainty a bit, but then you really have no information in that regard. And again, it's a type of uncertainty that exists, but that's not really quantifiable. In essence, that comes down to uncertainty due to model misspecification.
And we have just a final question. Is there a PSN package to compute CI and PI directly?
Oh, sorry. I do not have knowledge to answer that question. You would have to ask that to the package developers.
Okay, with that, I'm going to wrap this up. Thank you, Dr. Hu, for a fascinating and very informative discussion of variability and certainty. I have to admit, I really loved your slides where you defined what they were. I think that was incredibly helpful. And for all of our audience, Dr. Hu's paper is available. It actually came out online a few weeks ago. So I'd like to recommend everybody take a look and go ahead and read the paper and expand everybody's knowledge just a little bit. Thank you so much for the webinar, Dr. Hu, and we really enjoyed having you back to present this.
Thank you, Rebecca, and thank all the audience for the lively discussion.
Thank you. Have a great day, everybody, and we hope you come back and join us on a future webinar. Bye, everyone.
Bye.